Hello. All right, fourth one I'm doing today. Let's go. Let's talk about polar coordinate systems. So we've done a lot of work now being able to solve Newton's laws of motion, and we typically have been sticking with Cartesian coordinate systems, X, Y, Z, those sorts of things. Though Cartesian coordinate systems are not always ideal, particularly when you're dealing with circular motion. One example could be, if I'm just looking bird's eye view of, suppose there's a nail in the center and it's attached to a string. There's a ball that's then connected to that string, and I get it spinning on this kind of frictionless icy surface, so it starts spinning in a circle. I could set it up so that it's spinning, and then if I release it, since there's no friction, there's no horizontal forces, horizontal being kind of in the plane of the table, the thing, if it's spinning, presumably it should keep spinning, or keep trying to move in a straight line but going in a circle because of the string. What's going on here? Should be speeding up or slowing down? I don't know. But we can figure it out. But notice in this case, X and Y aren't really great if I'm analyzing my system of the ball. There is this tension from the string that we want to analyze. But notice that the direction of that vector is constantly changing as the ball rotates around. We could imagine that there's some angle theta. Theta is a function of time that is spinning around. And so the tension force that's pulling kind of towards the center of the circle from the string, that vector then is a function of theta, which itself is a function of time. And so writing in terms of its x and y components, in this case, is not terrible, but it'd be nice if it could be simplified. Particularly if you think about it, in this case where you have the ball on a string and it's spinning in a circle, the tension force always is pointing towards the center of the circle. And in this case, as long as the string is not allowed to change length, the velocity is also always perpendicular to that force vector. And knowing that force vectors create accelerations, and knowing that accelerations are how velocities change, and going back to the module where the perpendicular components change direction and not magnitude, there are things that are being said here by the geometry. We could also hope to write this down mathematically, but again, Cartesian coordinates might make it a little messy. There's going to be lots of sines and cosines flying around. Why not instead utilize the fact that the circular motion has a radial component, a part that's towards or away from the center of the circle, and then a tangential component, a part that is perpendicular to that radial line connecting the location of the particle to the center. This is polar coordinates. And then if you add a third dimension, it is called cylindrical coordinates. So the motivation is something kind of similar, that maybe I want to analyze this. There's a little hole in the center of this table, and there's a string with a bob of mass m. This string then goes through the hole and then is attached to another m that just dangles vertically in the middle of the table. And the question is, how fast do we need to spin the table mass so the hanging mass does not move? Right, this being the idea that you have some mass on a string, I can get it spinning, of course, And here, this is more like the first example, I'm anchoring its motion to my thumbs because I'm pinching the rope there. Notice here, there's tension in the part that's spinning. There's no tension in the rope that's just kind of dangling. You could imagine, though, I could hold the rope with a loop hand so that I'm not really doing anything to the rope. Then I can spin it as well. But I'm holding on to, I guess you can see my fingers, I'm holding on to the rope in the vertical part. Where if I were to let go, it would just zoom off in a straight line. Though it is possible that I can hold the rope with some amount of force such that it doesn't move at all. And so you could imagine replacing my hand here, this hand here, with some sort of hanging mass that has the same weight as the amount of force I'm using to keep the ball, both of these things, right, from flying away and from the mass that's hanging vertically from moving up or down. So that's the idea. How can we figure out this motion? What tension in the string is needed? So polar coordinates relies on not using x and y, though we will use Cartesian to motivate. But if I have a point that's located here, and I can talk about that it has a position vector that moves from the origin. If I think of this like a point on a circle that has radius r, then there is a radial location in terms of how far away it is from the origin, which is easy enough to figure out by the Pythagorean theorem, as it is a distance x away and a distance y away in both Cartesian directions. So the distance away from the origin, which I will call capital R, is then just Pythagorean theorem. It also, if I take the x-axis as kind of the definition of theta equals 0, and having clocks, the phrase is clocks are negative, where clockwise motion is negative, counterclockwise motion is positive. So I could define a theta value from the x-axis, where then tangent of that theta is then related to these y and x values as well. Or you could use another trig function if you want, like sine of that angle. SOHCAHTOA, opposite over hypotenuse, it looks like it's y over capital R or something like that. Similar for our cosine. The goal for polar coordinates is that rather than using x and y, I want to use capital R and theta. I want it to be a measure of how far away I am from the origin, plus how much I should rotate from some axis that I'm going to define to be theta, where theta equals 0. It doesn't have to be x. That's just traditionally what's done. And like I said, right, it's r and theta, right? So just by looking at this triangle, there is a relationship between the two coordinates where if I give you r and theta, you can figure out x and y. In this case, x is just r cosine theta, y is r sine theta. Or if I give you x and y, you can figure out r and theta by the two expressions I have on the left. The idea that if I, given x, y, I can do the Pythagorean theorem to get r, I can do an arctangent to get theta. Given r and theta, I can then calculate x and y by the trig functions, expressions. So this gives me a unique, it gives me two ways of describing the same location, one in terms of x and y, one in terms of r and theta. But these are being defined, right? R, right, square root of x squared plus y squared, tangent of theta is y over x. These are being defined in terms of the Cartesian x and y. What I want to do is I want to get rid of x and y. I want to get rid of the Cartesian axes entirely. And I want to have two different axes that correspond to the direction that's either towards or away from the center, which we'll put the origin at. and then how much it is rotated around some axis that we will define to be theta equals 0. So again, if I have some point here, right, this position vector, rather than writing it in terms of x and y components, I want to have an axis that points in this direction, which is going to be the radial direction, away from the center. And then, because I want the right-hand rule to be obeyed and all that fun stuff, I'm going to create a orthogonal axis and call that the theta direction. Similarly, if the particle then relocates to, say, right here, this then is the position vector. In this case, if you imagine the thing kind of rotating counterclockwise, this would be kind of the direction that's away, the positive direction away from the origin. And then, by the right-hand rule, the theta axis would point in this direction. So notice in this case, the axes themselves move along with the particle. The unit vectors r hat and theta hat are not constants, or are not stationary like x and y hat and y hat are. So that does make it a little bit more complicated. So if you write, for example, positions, right, to specify a position in x and y, you're saying something about how far to the left and right you go, and then how far up and down you go. To specify position in polar coordinates, that position really is just saying how far out do we have to go away from the origin along the radial direction. And that's position. Usually this r is a function of theta, which then tells you kind of where to place it. But again, by specifying theta in that sense, you're kind of translating back to Cartesian coordinates by doing that. If you really just want to talk about position in polar coordinates, you just have to tell me how far away you are from the origin, and that is your position in polar coordinates. If you want to orient it relative to Cartesian, you can translate it back, which again is just by the relationships above, looks like it's r cosine theta in the x hat direction plus r sine theta in the y hat direction. Or in this case, there's an r in both terms, I can factor it out. It looks like it's r cosine of theta in the x direction plus sine of theta in the y direction. Which, if you compare the top line with the bottom line, that looks like the unit vector in the radial direction. If you want a translation from polar to Cartesian, looks like this is the same thing as cosine theta in the x direction plus sine theta in the y direction. So we can use that as our unit vector in the radial direction. There are two axes, of course, that are perpendicular. So we also want to be able to specify what we think the unit vector in the theta direction should be. And it's not that hard to come up with an expression for this as well. And we did this where we kind of, essentially to define this, we realized that we kind of projected this unit vector onto a component that's along the x hat direction and the y hat direction. Similarly, you could take this unit vector and project it so that it has components along the x direction and the y direction by a similar looking triangle. In this case, you get that it should be negative sine of theta in the x hat direction plus cosine of theta in the y hat direction. I'll let you convince yourself that that's the case. So we have Cartesian versions of the two unit vectors we want to write down in polar coordinates, where everything is specified by r and theta. We ultimately, though, want to also be able to use this in, say, a Newton's second law context, which means we should be able to write down velocities and accelerations, namely, in polar coordinates as well. Because then I can write F equals ma, but the a I will use if I'm working in polar coordinates is going to be what we need to right now derive. It can't just be ax, ay, az, but it will be some radial acceleration, some tangential acceleration, and if there's a third dimension, some z direction. But let's stay with 2D for right now. And the thing why these are a little bit more involved is what I said before, is that the unit vectors themselves change in terms of their orientation as the particle moves around. Which means if the particle is moving around as a function of time, to describe it in Cartesian coordinates, you have an x and a y and a z, and those never change. You can always specify kind of how far you are along each of those axes. The axes themselves are moving. So based on what the particle is doing, that's also saying something about the rate that the axes themselves are moving, which means the time derivatives of these unit vectors are non-zero. So we can't blindly calculate velocities without also remembering that the unit vectors themselves change when you do things as a function of time. Let's try it out. I want to define velocity in polar coordinates, which again I'm going to define as the time derivative of position, which in polar coordinates is r hat. That is my position vector in polar coordinates. By the product rule, I'm going to go back to the dot notation now. This looks like it's r dot in the r hat direction plus r and r hat dot. Again, before when it was Cartesian, x hat dot, y hat dot, all those were just zero. Now we can't say that. We could go back up here and calculate the time derivative of this unit vector. Time derivative again. Important to remember. So the derivative of the first term looks like it's going to be negative sine of theta, but that's not it, multiplied by theta dot, by the chain rule, because these things are, the derivative is as a function of time. So it's d by dt, not d by d theta in the x hat direction, plus the sine becomes a cosine of theta dot in the y hat direction. And again, the time derivatives of x hat and y hat are zero, so we don't need to worry about those. Well, if you look at this, if you factor out the theta dot, it looks like it's negative sine theta x hat plus cosine theta y hat. Well, to me, that just looks like this entire thing is theta dot multiplied by the unit vector theta hat. So we now have the time derivative of the unit vector is theta dot y hat. How is the radial unit vector changing? Well, it's changing only in orientation. So it depends on kind of what's going on in the perpendicular sense. So it kind of makes sense that the time derivative of this unit vector should depend on something that's perpendicular to it. Similarly, the time derivative of this looks like it's going to be I'll just let you figure it out for yourself. Leave it as an exercise. And ends up being negative theta dot times the r unit vector, r hat. And again, you get that by product rule and chain rule. So then the velocity here, it looks like it's r dot in the r direction plus r, and then the derivative of this unit vector we just said is theta dot in the theta direction. So it looks like in this case it's r in the r hat direction plus r times theta dot in the theta direction. And this is a general expression for velocity in polar coordinates. No assumptions about uniform circular motion or that it's even moving in a circle. I could take a line and write it down in polar coordinates. And this is the general velocity. I need to know something about r, which is a function of time, and I need to know something about theta, which also is a function of time. In the case of velocity, the derivative of, oops, I'm missing a dot. In the case of, both r and theta's derivative appears in velocity as well. Let's see, position, we'll highlight velocity, we will highlight. And just to get some terminology out of the way, theta dot, what unit should it have? Theta is units of radians, or dimensionless. So theta dot should be radians per second. This is what's usually called the angular velocity. I think typical intro sequence books likes to use omega for angular velocity. But really, this is the time derivative of the angular position, theta. And again, we should try to get better at interpreting what this means. This first term is pointing in the radial direction. So it's talking about radial changes in motion. If I draw quick axes here, here's a dot, here's a position. If the velocity is pointing, say, straight up, so that the position vector might start here and it might end up here. Well, notice that as it traverses from the start to finish, it's getting farther away from the origin. So there's a radial change. There's a change, at least rather, in the radial distance from the origin to that particle. That's this first term here, r dot. How much is the particle changing radially in terms of its location from the origin? And then there's the tangential part, which might be saying something about how it's rotating relative to the axis where theta is defined to be 0, which might be, say, this. So a part that can be getting it closer or farther away from the origin, and a part that might be moving it tangentially around, maybe in a circle, maybe in some other periodic shape. All right, what about acceleration? Which is going to be the derivative of the velocity vector. Which again, for completeness, the derivative of this entire thing. Well, product rule away. The first term looks like it's going to be r double dot r hat plus r dot r hat dot, and then r dot theta hat plus r theta double dot theta hat plus r theta dot theta hat dot. Oof. Which then, what do we do? So this first term looks like it's just the same. The derivative of this unit vector we said is theta dot times theta hat. This looks like it's already done. Notice it's the same as the previous term. Then we got r theta double dot. You might call this angular acceleration in theta direction. And then minus r, another theta dot pops out, so it's theta dot squared in the r direction. And there's that minus sign as well. If we want to lump everything together, group all the r hats and the theta hats, this looks like it's r double dot minus r theta dot squared, all in the r hat direction, plus, looks like r theta double dot plus 2 r dot theta dot in the theta direction. And this is the general expression for the acceleration of an object when written in polar coordinates. Some of these terms might look familiar. Again, this is just kind of radial acceleration. It can change just by the fact I can get, I might be accelerating. I might have a motor that's pushing me farther or closer to the origin. This term here is called the centripetal term. This is kind of what you might remember from an intro sequence when you wrote stuff like, tau equals I omega for torque and rotation, right? Or not omega, I alpha for angular acceleration. That angular acceleration term, right, might look something like this. And then there's this term, which is the Coriolis term. And the centripetal, sometimes I think it's also called the centrifugal term. I actually now forget if it's centripetal or centrifugal. Doesn't matter. Those are the kind of terms that appear when you, going back to the previous module, when you try to do physics in a rotating frame. Polar coordinates makes a lot of sense, and naturally dealing with the rotation of the Earth, for example, pops out terms like that centrifugal, centripetal, and the Coriolis terms. But those are just names. This acceleration, this big messy acceleration that has two terms for each of the coordinates, is what you use in F equals ma. When you're working in polar coordinates. If you are working in polar coordinates, the A you use on the F equals ma expression is this whole mess. And typically there are also geometric considerations you can have that will allow you to, for example, eliminate some of these terms. In general, this looks like a set of two coupled differential equations that are both second order. There's a differential equation for r, which might involve theta and theta dot within it. And there's also a second order differential equation for theta, because there's a second derivative for theta, but then that expression for on the right side also combines r and its derivatives. So these are coupled. You more or less have to find r and theta as a function of time simultaneously, unless there are assumptions that help you out. Again, this is the most general way to write it down. Let's go back to our problem now and see how things might simplify for our bob on the spinning table. So again, two masses m, this thing is spinning, and I don't want the thing to rise up or down at all. First thing I might do is, if the thing is not rising up or down at all, a force analysis for the hanging bob. All the motion is vertical. I know there's going to be a tension force pulling up. Its own weight is pulling down. And if nothing's moving, there's no acceleration, so that better be zero. So this then is establishing that the tension is equal to m times g in the rope. That tension then is uniform throughout the string. Now if we go, and that wasn't in polar coordinates, of course. Now if I go to the thing that's hanging, or sorry, not hanging, the thing that's spinning around on the table, and I now want to analyze this thing as it spins counterclockwise. Again, I could use Cartesian, but why, when I could use polar coordinates? So I'll put my origin at the hole, and then I'll have this be the position, and then this be the tangential component, which again are going to move around as the thing moves around with you. But in this case now, if you imagine as the thing spins around and the axes move with the particle, the rope always points in the radial direction. It always points towards the center of the circle in this case, which is where this coordinate system really gets a benefit. So if I want to write down the tension in polar coordinates, then I need an r direction and a theta direction. In this case, then I expect it to just be negative t in the radial direction, and then 0 in the theta direction. And again, so it's not confusing, right? This is negative t r hat is all that is saying, plus 0 in the theta direction. You have to know what coordinate system you're talking about before you start thinking about what these coordinates represent. And why negative t? The convention, as I wrote it down with the equations before, is that away from the origin or away from the center is assumed positive, towards the center is assumed negative. So since the tension is pointing towards the center of the circle that's being traced out, or the origin, we take that to be the negative direction when talking about radial directions. If there was a theta component, then it's just based on the orientation of the theta hat direction. Okay. So for the spinning ball on the table, F equals ma in polar coordinates is the following. Well, I should ask, is there any other forces acting in the plane of the table? And there's not. The table, of course, has a contact force, but that's pushing out of the page. And that is being balanced by gravity. You don't need polar coordinates to do that component, but this part, the spinning part in the plane of the table, we're going to use polar coordinates. So the net force then is only the tension, so it's negative t, comma 0, and the r in the theta hat direction. And then this equals ma. But again, the a we use here is not ax, ay, not even ar, a theta, but r double dot minus r theta dot squared, comma, r theta double dot plus 2 r dot theta dot. And now I need to solve for what these are as functions of time, perhaps, if I want to solve this problem, which as written might seem very, very daunting to figure out what this is. However, in this case, some simplifications can be made, right? If the hanging bob is not moving up and down at all, the length of the string on the table is constant. The thing that's spinning on the table is not getting closer to the center, nor is it getting farther away from the center. That means the circle it's tracing out has a fixed radius. And again, that's one of the coordinates. That's capital R. So R in this case is a constant, some value, call it R naught. Where this helps us, though, is that the derivative of a constant is 0. So that also means the derivative of R is 0. That also means the second derivative of R is 0. So this gets us the first simplification, where this force equals m. And now I can see what simplifies. R double dot, gone. And it seems like it's only r theta dot squared that's left. So r theta double dot, but then plus 2 r dot is 0, gone. So now this thing is simplified already a lot. Now it seems like it only involves derivatives of theta. So now let's see if we can actually solve this thing. If I look at the theta component, the second component, that looks like it says 0 equals m r theta double dot. R we said is a constant, so I'll write this as r naught instead. M and r are constants, so this looks like it's saying 0 theta double dot is 0. Which I can take the integral of that, because this is the same thing as d by dt of theta dot. So if the acceleration is 0, that means the velocity, or if the angular acceleration is 0, the angular velocity then is a constant. Maybe we'll use the intro sequence books, call that omega naught. The angular velocity better be a constant in this case. Well, then it seems like we're done. Because then the r component says that negative t equals m, there's a negative on this side too, r theta dot squared, but theta dot is omega, and that's a constant. R is a constant. So it looks like in this case it's saying that t equals mr omega squared. But t was just equal to mg. The g's cancel, so it looks like r omega naught squared equals g, or that the angular velocity that we need is going to be the square root of g over r. If I get it spinning with that angular velocity, the hanging bob will neither rise nor fall. I feel like I lost in... Nope, that's good. I have a typo in my notes. All right. We could ask about what the velocity of the ball needs to be, but that's not too bad either, because we have an expression for the velocity, which was r dot comma r theta dot. We said r dot was 0, which that makes sense. There's no velocity in the radial direction because it's not getting closer to the origin or farther away from the origin, but it is moving tangent to that circle at a rate of r times omega naught. So the velocity in this case is purely tangential and is equal to r omega naught in this case. So again, that might seem familiar. The radius times the angular velocity is the linear velocity. And again, it's just popping out naturally in this case where we realize you are constrained to moving on a circle. In this case, this is also an example of uniform circular motion, that the velocity is a product of two constants. It does not change. The velocity is purely azimuthal, where the acceleration vector we wrote down is purely radial. It looks like it's going to be negative m r omega naught squared, comma 0. The acceleration is purely radial and it's negative, so it points towards the center of the circle. That's the whole idea with center-seeking forces in centripetal motion. It goes towards the center of the circle. And if the velocity is always perpendicular to your path, that only can change the magnitude of v, that can only change the direction of v, not its magnitude, and you get uniform circular motion. Let's write down some constraints, or let me write down some relationships, and maybe I'll call it instead of doing this other example. Just as a way of summarizing this. In general, we just said how you can write down the velocity in polar coordinates has a radial component and an azimuthal component or tangential component. The acceleration gets a little bit more complicated, but isn't too bad. And that's general. You can always start here. And if you have reasons that you can logically say something about these derivatives, that usually simplifies your life. For example, one simplification is maybe you're constrained to move on a circle. Right, something about the setup has been established so that you can't not be on a circle. Like I pinch my finger at a certain location. So as I spin it around, this thing can't get closer or farther away from my hand. It's constrained no matter what I do. I can speed it up, I can slow it down, of course, but it is nonetheless constrained to move in a circle. Well, again, mathematically, what does that say? To move on a circle means that r is a constant, which means that r dot and r double dot better be 0 if that's going to be the case. So if you're constrained to move on a circle, the velocity simplifies in this case to 0, comma, r theta dot, and the acceleration simplifies to negative r theta dot squared, comma, r theta double dot. And if you write the velocity as 0, comma, and I write just this as v, not as a vector, since the velocity only has one component, that component that's tangent to the circle, you can rewrite the acceleration as well, right? I can take the first term, multiply and divide by another factor of r, and then use that r times theta dot is v, and this first term then becomes negative v squared over r, comma, r theta double dot, if you want to write it that way. And that also might look familiar, v squared over r. Again, just popping out very naturally by this way of writing it down. If you're constrained to move on a circle, plus uniform circular motion, then r is a constant still. So r dot and r double dot are 0. But uniform circular motion implies what? That means you're going around the circle at a constant rate. There is an angular velocity, of course, because the theta is changing if you follow my finger, but it's not speeding up or slowing down as it does that. So that suggests that theta double dot is 0 as a result. In this case, then, the velocity ends up being, or you might then write this as that theta dot is a constant. Maybe we'll call that omega naught again. Then the velocity looks like it's 0, comma, r times theta dot, which we just said was r times omega. And then the acceleration then is minus r omega squared, comma, 0, since theta double dot is 0. Or again, you could write this as minus v squared over r, comma, 0, if you want to. The good old uniform circular motion results from, the good old days of the intro sequence. So if you have these geometric constraints, right, you could always start here. This is super general, always true. But then if you know you're stuck moving on a circle, but maybe you can speed up and slow down while on the circle, well, geometrically that implies this, which then simplifies the acceleration velocity to the following. If you're constrained to move on a circle and it's uniform circular motion, then that's the most constrained. That's saying that there's something about r and its derivatives, and they're saying something about the derivative of theta and theta double dot in that case. So suppose you are on a cart. And you're moving horizontally until you come to some vertical loop, in which case then you go over the loop, hopefully, and come out the other side. And we want to analyze the motion of this person as it goes around the loop. Now, if you've ever been on a roller coaster, you know that your speed changes as you go around this loop. So it's not uniform circular motion, if this was a vertical loop, but it is circular motion, where you are constrained to move on a circle. So to me, that suggests, why not use polar coordinates to at least study the motion of the object as you, which will give you mass m, as you enter the loop, which will have radius capital R. So we can define a coordinate system of course r and theta. And maybe I'll take vertically downward to be where theta equals 0. So by the time the cart is here, that corresponds to this theta here. So immediately at the bottom of the circle, let's call that theta equals 0, and then theta increases as you go around until it gets to 2 pi, and then you're done. Let's focus on just the loop, and suppose that is the location that you're at. So in this coordinate system that I'm going to center in the middle of the loop, there's my value of theta. The system I'm studying is me on the cart. And I could ask what forces are at play. Well, I expect there to be a gravitational force, of course. And then, since I'm touching the ramp, or I guess the coaster, we'll just stick with ramp, that there is a contact force between me and whatever the cart is touching the ramp here that is going to be pushing away, which happens to be, since this is a circular loop, always towards the center of the circle, which is fantastic, because then I can write F ramp is going to be something like negative F, which itself might be a function of theta. Well, maybe, since we all love normals, right? There is the component that's normal to the loop, or the ramp, and there's nothing that's pointing in the azimuthal or tangential direction. Again, this is a benefit of us using polar coordinates, because then this force is entirely restricted along the radial direction. It always points towards the center of the circle. Center of the circle, hence why the negative sign. The gravitational force always points straight down. So sometimes that's purely radial, like when the cart is at the very bottom of the circle or the very top of the circle. Sometimes it's perpendicular to where the cart is, like when it's on the leftmost or the rightmost part of the circle. So we do have to do some trig triangles to break negative mg, which is what we would have written before, but that's in the vertical direction, to having a radial component, which looks like it's going to be mg cosine of theta, and then a part that is perpendicular or tangent to the circle, which looks like it's going to be negative mg sine of theta. And again, you can think through that. If you have, this is theta, we just said that this is the radial direction. Right, that's kind of where the cosine comes from for the radial direction. And then to obey the right-hand rule, this is the theta direction. You can figure out that that must then be the sine component. And the negative sign, because if I project this vector onto the theta hat direction, notice it's pointing in the opposite direction as the unit vector, hence the negative sign. All right. And we know also that we're constrained to move on a circle, so I expect these two derivatives to vanish. So then F net equals ma. The radial component looks like there's going to be an mg cosine of theta minus n, which itself is a function of theta, theta being a function of time. And then the azimuthal part, the tangent part rather, negative mg sine, then there's nothing for the ramp. Then that equals the mass of the cart. And then r double dot goes away, so this looks like it's negative r theta dot squared, and then r theta double dot, and then the 2r dot theta dot term vanishes. Now, this, unfortunately, is very challenging to solve analytically. If I just look at the r direction, I could divide through by m. It looks like this is saying that g cosine of theta minus n of theta, well, I won't divide by m, mg cosine theta minus n equals negative mr theta dot squared. Looks like it's a first order differential equation for theta, because it's only the first derivative that appears. But it also involves this unknown n from the ramp. And then the second equation looks like it's negative mg sine theta equals mr theta double dot. I can divide through by m, I can divide through by r, and it looks like the second derivative of theta as a function of time is negative g over r, both constants, sine of theta. Theta, remember, also being a function of time, hence the second derivative. This is not a trivial differential equation to solve. It involves Jacobi elliptic integrals and things get complicated. My initial conditions, I also know that theta at t equals 0, let's call t equals 0 when you're at the bottom of the ramp, so that's going to be 0. And then theta dot at t equals 0 is going to be whatever my initial angular velocity is, which I might call whatever my initial velocity is divided by my radius. In that case, if I enter the ramp with a horizontal velocity v naught. This whole thing here only depends on theta and its derivatives, since r itself is a constant. So while this is challenging to do analytically, we can do it numerically. Whip out your Python ODINT and solve it with a Runge-Kutta method. Let's suppose you do that. So you can then numerically solve for theta as a function of time, as well as theta dot as a function of time. Given theta dot as a function of time, you can then use the other equation to compute n. Because notice n as a function of theta then is just, where is it? I've lost it. Looks like it's going to be mr theta dot squared plus mg cosine theta. Which, again, if you numerically find theta as a function of time, which let's do some highlighting. If you numerically know theta as a function of time, as well as theta dot as a function of time, you could plug those in and numerically get an expression for n as a function of time in that case. So I did this numerically just to show you some results. So here is one where, let's go through these slowly. So let's just look at the left. So this is showing you for a given initial speed. So I think the numbers I use is I let little g be 10 meters per second squared, and I let m and r both be 1 kilogram, 1 meter. And then I had an initial velocity as you enter the loop of 5 meters per second. No, that can't be true. This has to be 10 meters per second, sorry. Because then my initial angular velocity then is 10 meters per second divided by 1 meter. So 10 meters per second was my initial velocity. Then I crunch through the differential equation and I get a curve for theta as a function of time, that's the blue, and then theta dot as a function of time, that's the orange. As a function of time, and then the y-axis could be either radians or radians per second. So again, what does this say? Do you make it through the circle? Right, it looks like your theta as time goes on increases. Looks like it's kind of curved a little bit. There's a little bit of curvature. Then you get to theta equals pi. So that you've made it to the top of the loop. And then you start coming over the other side. Theta is still getting bigger. And then eventually you make it to 2 pi, which is the bottom of the loop. Presumably that's when you would exit and go off. The differential equations don't know that, of course, so then it just starts to repeat itself. So this looks like you do make it over the loop. And then you can notice your velocity. You start really fast going up the loop, and then you slow down. That makes sense. Gravity's kind of slowing you down as you go up. And then once you make it over the other side, you start to speed back up and up and up again until you get to 2 pi, and that starts to repeat itself. Given those, I can plug that into the expression we wrote down for the normal force, and I can actually compute what the ramp is doing on the coaster as a function of time. And you can see that the normal force, in this case, the normal component rather, the contact force between the ramp and the cart is not constant. It changes. It has to really push up against the cart at the start, because not only does it have to change its direction, it has to win out, is to do that on top of gravity trying to pull it in the opposite direction. Then when you get to the top, notice that here it kind of corresponds to this time here. Then gravity is working with you. At the top, the cart is being pulled down by gravity, and it's also being pushed down by the track. So they both are working together to change your direction while keeping you on the circle. All right, so the ramp doesn't have to, or the track doesn't have to do as much. And then it starts to repeat itself. How does this change now? If the only thing I'm going to change now, instead of starting at 10 meters per second, I start at 5 meters per second. Well, then I get a plot that looks more like this. And here we have to interpret what's going on. Theta is a function of time. You're getting up and up and up. You're climbing the ramp. But then notice you plateau, and you never make it quite to theta equals pi. So you're going up the ramp, and then you kind of don't quite make it all the way up the ramp. And then it looks like theta starts to decrease. Again, this is being derived and calculated on the assumption that you're stuck on the circle. So this is on the assumption maybe that the track has anchored you, right, so that you can't fall off. And then notice how that corresponds to your angular velocity. Very positive, you start moving up the ramp. Eventually, you hit 0, which notice at that point, you then start with a negative angular velocity, and you start to move back down the ramp. You don't make it over the hump. Now the normal component, given these, notice something interesting happens. The normal component, right, is always pushing you away from the track towards the center of the circle. Should have thrown a negative sign maybe in here to use polar coordinates. That's okay. Notice that it's very positive and then gets smaller and smaller and smaller like we saw before. But unlike the previous one, where it always was some positive number, in this case it eventually goes to 0 and then becomes negative. What does that mean? Remember, 0 means is right when the things kind of lose contact with one another. A 0 component means that rather than pushing the cart away from the ramp, it's somehow hooked in and is pulling it towards the ramp as well. So in this case, this is where, say, hooks on the track would have to be pulling the cart onto the track in order to make sure that you don't fall off. Or if those hooks didn't exist, then actually this part is where this solution would become inaccurate. Because at this point here, which looks like at about a half a second, is when the cart would actually just fall off the track. Remember, this was built in with the assumption that you're constrained to move on a circle. But if you weren't really constrained by engineering to stay on a circle, this point right here is where the cart would just fall off the track, which would not be so good. So there's a minimum velocity you need in order to make it over the track, which takes you one line of math if we knew about energy conservation. But we can numerically calculate these things, and if we were to build a coaster, we could figure out how much, how much force we would have to anticipate being able to provide or withstand, if the track had to deal with these sorts of motions. All right.